Okay, so welcome to Chapter 2, Section 2.2. In the last section, we briefly talked about the density curve. In this section, we're going to be taking a look at how the normal distribution is related to the density curve. So by the end of this section, you will be able to describe and apply the 68, 95, and 99.7 rule. So by the end of this section, you'll be able to describe and apply the 68, 95, 99.7 rule. You'll be able to estimate the relative locations of the median and mean on a density curve, understand and describe what the standard normal distribution is. All right, so there's sort of a key word here, standard. All right, so we're going to understand what the difference is between the standard normal distribution and just a normal distribution. You're going to be able to perform normal distribution calculations on your graphing calculator and by hand and assess normality. All right, so let's just take a quick look at density curves. Whether or not in Chapter 1, we developed a kit of graphical and numerical tools for describing distributions. So that was graphing our distributions, and then we took a look at SOCs, and we explained the center of the spread, the outliers, and the shape using both a numerical analysis and in context of our problem. Now we're going to add one more step to this strategy. The question is, what are we going to add? All right, so in the last section, first thing we said to do was you always want to make sure you plot your data, make a graph. We're going to look at the overall patterns. What is the shape, the center, the spread, and the outlier SOCs. So just remember, this is a quick refresher when you're making your box and whisker plot. Make sure you show those calculations for your outliers. And then we calculated a numerical summary to briefly describe the center and the spread. So that was our 5-number summary. We took a look at the mean and the standard deviation, and then we also decided what was the best way to measure the center and the spread. Was it the mean or the median, and the standard deviation or the IQR? So what specifically are we going to add to these 3 steps? What we're going to add specifically is sometimes the overall pattern of a large number of observations is so regular we can describe it by a smooth curve. So basically what we're going to be doing is we're going to be taking a look at a histogram, creating that histogram, and seeing if we can draw a nice smooth curve over the top of our histogram. All right, so what exactly is a density curve? We briefly just took a look at it in the last section, but let's get a little bit more in depth of what exactly a density curve is. First of all, a density curve is a curve that's always on or above the horizontal axis. Okay, so let's take a look at this curve. We're taking a look at the vocabulary score of 7th grade students. We plotted a histogram. So with a density curve, all we're doing with that histogram is seeing if we can sort of draw this nice smooth curve that goes on top of the histogram. Can we sort of encompass most of the area of the histogram by a nice smooth curve? That's all a density curve is. If you notice, it's always on or above the horizontal axis. Okay, so look, it never dips below the horizontal axis. It has an area of exactly 1 underneath it. And think about the reason why would this have an area of 1 underneath it? Because if we take a look at all of our data, if it's a density curve based off of data, 100% of the data has to be underneath that smooth curve. So the area is always going to be 1. What a density curve does is it describes the overall pattern of the distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of observations that fall within that interval. All right, so really all that means is if I take a look at an interval of values, let's say from 4 to 6, okay, so the area under the curve describes what percent of observations fall between 4 and 6. So that's just a fancy way of saying, let's look at a portion of the curve. Okay, what percent of the observations fall above 8? What percent of the observations fall above 6? What percent of the observations fall between 2 and 12? Well, pretty much 100%, because 100% of my data should be under the curve. So this is just a density curve that's looking at the overall pattern of a histogram of the scores of 947 7th grade students in Gary, Indiana on the vocabulary part of the Iowa test. I don't know if you guys remember taking the Iowa test in 4th and 5th grade. All right, but the scores on the Iowa test can be described by a smooth curve drawn through the tops of the bars. Okay, so this is our density curve right here. Okay, so what exactly do you need to know about the density curve? What are we going to know as we're working through the next couple of units? All right, number one, the density curve gives a good overall description of the overall pattern of the data. So if we take a look right here, we're taking a look at sulfur oxide and the density of sulfur oxide. All right, so when we draw this smooth curve, it gives us an overall pattern of the description. All right, so when I draw that curve, it's pretty much, I want it to sort of try to go through the tops of the bars. It's never going to be perfect. So this is where you're going to look and say, oh, is it approximately symmetrical? When I draw my smooth curve, is it skewed to the right? Is it skewed to the left? Is it bimodal? Is it unimodal? Is it uniform? So it just gives us a good pattern of our distribution. Outliers are not going to be described by our curve. So let's say we have a point all the way over here, all right? Our curve is not going to describe that overall distribution with the outlier. So we're just going to encompass most of the data. So the outliers are not, if we have an outlier over here, we're not going to make this a really long tail so it looks like it's right skewed when in fact it's not. It's always an approximation. No density curve is ever going to be perfect. All right, so our density curve is never going to fully get every single exact data point. All right, so if we notice here, we have sort of a little gap here, but that's maybe, then the area of this missing portion is taken up by these areas that we sort of missed. Okay, it's just an approximation. It's never going to be perfect because everything in the real world is not a perfect situation. So most of the time when we do this, we're going to be using the normal family of bell curves to describe distributions. There are a variety of shapes. I'm sure you've heard the normal bell curve before. So when teachers talk about curving tests, they do it according to the bell curve. All right, so in this section, anything that is a normal bell curve, that's what we're going to use to do our calculations. So what exactly does the area under the curve look like? Remember that area has to have a length and a width. All right, so it has to have a length and it has to have a width. So if I wanted to find the area to the left of about 15, what percent of the curve is less than 15? All right, so every time we talk about density curves, we're always talking about area. So in order to find the area under the curve, we must have a range of values less than 15, between 10 and 20. That's an area. Okay, can shade that in. We cannot find the area of just one value because it's not going to have any width. So what is the area at 20? Well, the area at 20, there's this height right here, but there's no width. So anytime we're looking for values under the curve, we must have a length and a width. It must be a range of values. Even if it's between 20 and 20.5, that's still a width of 0.5. All right, so if we take a look at this specific example, the shaded area under the curve is 0.3 or 30%. So that tells us that 30% of my entire 100% of my curve is shaded in. Okay, and that's an area, all right, because it's an interval from 0, or basically sort of like negative infinity, up to 15. All right, so in the previous section, we took a look at the mean versus the median. So let's take a look at what the mean versus the median look like in a density curve rather than just a histogram. Well, not a surprise, they're going to be similar since the density curve and the smooth curve that you're drawing is actually coming from the histogram. All right, so let's first take a look at the median. So remember that the median means there's equal areas of mass on either side of the median. So if we have a perfectly symmetrical curve, our median's in the middle, the area to the left and the area to the right are going to be the same. So that's going to be 50% of your data and 50% of your data. All right. If it's not perfectly symmetrical and you have a graph that's skewed to the right or skewed to the left, think about your median as where most of the values lie. All right, remember your median is always going to be where most of your values lie. The mean is going to be pulled more towards the tail. So if we take a look at our median right here, the area to the left of here is going to be 50%. The area to the right of here is going to be 50%. Let's take a look at our left skewed graph. Our median, once again, is sort of where most of your data lies because it's a typical value. All right, and then our mean is going to be to the left of that because it's pulled down by that long left tail. So the area to the left here, to the right here is going to be 50%. The area to the left over here will be 50%. It's always in the middle. How is that different than the mean? Okay, remember that the mean is our balancing point. So think of like your seesaw. How am I going to average it or balance the weight out on a seesaw? It's the balancing point as if it were a solid mass. If the curve is skewed, then the mean, remember, is not resistant to outliers. So if we look over here, the mean is pulled towards that skew. Okay, so it's going to change. It's going to make the mean lower than what it actually is. It's not necessarily a good measure of center. Okay, it's going to be pulled in the direction of the tail. So in each of these graphs, these each represent the mean. Okay, so if we take a look at this one right here, here's our mean. It's a balancing point. Okay, it's where my graph is perfectly balanced. Over here, if we put the mean, all right, so if I put the mean in the wrong direction, I'm moving my balance point here to see where it's going to balance. It's going to balance right on the mean. Okay, so this is sort of like my seesaw. I'm moving along the curve until I have equal, a nice, sort of center of gravity where it's balanced on both sides. All right, so how do you know exactly where the mean and median are located? Well, hopefully from the last section and the couple of slides that we've gone over, this should be relatively easy. All right, so remember, if it's symmetric, your mean and your median are right in the middle. Okay, we can use both of them to measure the center. However, most of the time we're going to use the mean. So really only use the median if you're talking about a graph that's skewed. Okay, the other one is a left skew graph. So remember, the mean is less than the median. The left means it's less. The mean is less. So two L's. Use the median as the measure of center. We've already talked about this. Once again, just draw your median right where most of the graph is, and then draw your mean towards where the graph is skewed, because the mean is going to be pulled in that direction. What does it look like for a right skew graph? Okay, the mean is might, it's mightier. All right, so the mean is greater than the median for a right skew graph. The right, also you can say the mean is might. Okay, so if we take a look here, if we draw the median where most of the graph is, or the typical values, the mean is going to be pulled down by the tail. And in this case, we're going to use the median as the measure of center because it's a better representation of your typical value. I personally would not try to memorize this. Honestly, what I would do is I would remember that the median is where most of the data lies and the mean is closer to the tail. So draw your curve, put your median where most of the data is, and then put your mean a little bit closer towards the tail because you know your mean is going to be pulled in that direction. Look at your graph and then decide, oh, it's easy to see the mean is less than the median, the mean is greater than the median. All right, so let's just get some practice with some density curves. So many random number generators allow us to specify the range of the random numbers to be produced. Okay, so this is like on your graphing calculator if you're going to produce random numbers from 0 to 15. Suppose that we specify that the outcomes are to be distributed uniformly between 0 and 2. So remember what uniformly means. That means that everything is going to be the same height. So when I draw my histogram, everything will be the same height. That means I'll have equal numbers between 0 and 2. So the same number of zeros, the same number of ones, and the same number of twos. The density curve of the outcomes has a constant height between 0 and 2. So if I'm drawing the density curve, it's going to have a constant height because I have the same number of zeros, ones, and twos, and it's going to have a height 0 elsewhere. Let the random variable y be the value generated by the computer. All right, so what I want you to do is try to draw what that situation looks like and then figure out what is the height of the density curve between 0 and 2. Draw a graph of the density curve. Okay, so just take a minute and try that. Pause the recording and see if your answer matches what I have. All right, so let's check it out. Okay, so we have our density curve is from 0 to 2. We know it has a uniform height, so it's all exactly the same height. How did we get a height of 1/2 here? How did we figure that out? So remember, okay, a density curve must have an equal area, an area equal to 1 square unit. So if I was to color this in, I know that this would have to be 100% of my data, or it would have to be equal to 1. So if we look at the dimensions of the rectangle, okay, we know it has a width of 2. 2 times what number is going to give me 1? So 2 times what number is my height, which is 1/2, is going to give me 1 square unit. Now I know that this isn't like a pretty curve, like a normal curve. That's fine. It's still a density curve. It just so happens that it is a uniform density curve. All right, so using your graph that we just took a look at on the previous page, and the fact that the areas under the curve are proportions of outcomes, find the proportion of outcomes that are less than 1. So hopefully you have that graph sort of drawn on your paper somewhere. Take a few minutes and see if you can find the proportion of outcomes that are less than 1. All right, so let's just take a look. Now notice I have this probability statement. I want you sort of get used to that. We're going to be talking about it later on. Notice how this says the probability of y is less than 1. So we had defined y earlier to be the proportion of outcomes under the curve. So we want the probability that y is less than 1. All right, so if we're taking a look, if we just were to shade everything in less than 1, what is that area? All right, so what is the width? Okay, the width is from 1 to 0, so it's a total of 1, and the height is 1/2, so 1/2 times 1 gives me an area of 0.5, or 50% of the curve. All right, so try the next one. Find the proportion of outcomes that lie between 0.5 and 1.3. If you need to, pause the recording before you check out your answer. All right, so let's see how you did. All right, so we have our density curve. All right, so, and I would always suggest drawing and shading in the area, so it's a very easy visual for you to see exactly what you're looking for. Once you have the visual, I think it's much easier to write your probability statements. So we have 0.5 to 1.3. So this is the area I want to find. I've shaded it in yellow. Next is our probability statement, or our proportion statement. What's the probability that y, or our proportion, is between 0.5 and 1.3? Okay, so what is the height? The height is going to be 1/2. What is the distance from 0.5 to 1.3? Well, if I subtract 1.3 minus 0.5, that's going to give us how wide this is. And if I multiply 1/2 by that number, it's going to give me 0.4. Okay, so let's take specifically a look at normal distributions and the density curve. All right, one particularly important class of density curves is the normal curves, which describe a normal distribution, and that's what we're going to be using basically for the rest of the course. So this chapter is really, really important because we will be coming back to it again and again and again. So it's really important that you understand exactly what a normal curve is and how it describes the normal distribution. So let's just take a look. I have two examples of normal curves down here. So all normal curves are symmetric, single-peaked, which means unimodal, and bell-shaped. They don't all have to look exactly the same. If you notice, this one is a little bit wider, okay? It doesn't have quite the height that the other curve does. If you take a look at this one's much skinnier. The data is more compacted closely together towards the mean or the middle. All right, and this one, the data is a little bit more spread apart. But the important part is that it's symmetric, single, peaked, or unimodal, and bell-shaped. A specific normal curve is described by giving the mean and standard deviation. Now, take a look at these symbols. Notice how you have the symbol mu, that's your population mean, and this is sigma, which is your population standard deviation. So get used to drawing it this way. Draw your normal curve, and then in the middle, draw the mean, all right? And then label it. Label it exactly what that mean is. And then remember, your standard deviation is always the distance from the mean, all right? So you're going to have your standard deviation above the mean and your standard deviation below the mean. And we're going to group the standard deviations into 3 groups above the mean and 3 groups below the mean. So here's just 2 normal curves. The normal curve is most of the time going to show the population mean and the population standard deviation. So that's why your symbols are important. So whenever you write that, you would write mu equals, or if you wrote x bar equals, they would know whether you're talking about the mean or the population mean or the sample mean. Notice, if you just take a look, I mentioned this briefly, that the first graph, the standard deviation is much larger, so the curve is more spread out. So the average distance from the mean is further than our second curve. The second curve, the standard deviation is smaller, so the graph is a lot taller. Okay, so that means the average distance from the mean is a little bit less. Okay, so let's just take a little bit more of a look specifically at the normal curve. So remember that we had talked about earlier that the mean is located at the center of the curve. So when you draw your normal curve, you always want to draw your nice smooth curve, draw a line down the middle, and label the mean. Remember that the mean can change. So remember when we had talked about adding or subtracting 5 points to stat scores? So we can change that mean and it would increase by 5. But remember, when we take the graph and physically move it to the right or left 5, it's not going to change the standard deviation. All right, so we can change the mean, we can add or subtract it, scooch that curve right along the horizontal axis, and it's not going to change the standard deviation or the spread of my curve. The points on which the change of curvature takes place. So if you remember this from calculus, so if we take a look here, all right at this point down here, my curve, instead of going down, is starting to curve up. Okay, right here, if I start at the top, I'm going down. At this point right here, my curve is starting to sort of go back up again. They are called inflection points. It's an inflection point because it's the way your graph is changing concavity from concave down to concave up. This always takes place at one standard deviation above and below the mean. So here's my two inflection points. So concave down, I hit that point, it starts to go concave up. Remember, all of these properties that we're talking about are not necessarily properties of all normal curves. We're specifically talking about a normal distribution. All right, so remember, a normal distribution is unimodal, bell-shaped, okay, and has this nice smooth curve. Right, so a couple more things about the normal distribution. So we didn't actually have the official definition of a normal distribution. So a normal distribution is sort of like a subcategory of the normal density curve. So we have a normal density curve, and then from the normal density curve, we talk about a normal distribution. So any normal distribution, the reason that it's specifically a normal distribution is because we are defining the curve by the population mean or the sample mean and the standard deviation. That's why it's the normal distribution. That's how it's different than the normal density curve, because we are defining it specifically by the mean and the standard deviation. The mean of a normal distribution is the center of the normal curve. So like I said, you're always going to draw that nice curve first and put that mean right down the center. The standard deviation is the distance from the center to the change of curvature points on either side. So basically your standard deviation, remember, is from your mean. Okay, so then we're talking about from the mean, what is the average distance above the mean? What is the average distance below the mean? That was your inflection points. We're able to abbreviate the normal distribution with mean mu and standard deviation sigma. So whenever we talk about something being normally So whenever we talk about something being normally distributed, you'll often see this little sort of squiggly mark, and then n, and then maybe 5, 0.3. So that would tell us that it's approximately, so that sigma means approximately, okay, approximately normally distributed. We know it's a normal distribution because it's giving us the mean, which is 5, and the standard deviation, which is 3. Okay, so just a couple of examples of what could be normally distributed. So normal distributions are good descriptions for lots of real life data. Okay, so normal distributions statisticians use all the time. So statistic scores are usually normally distributed. There's a piece in the center that's it's symmetrical, it's single peaked, and it's approximately symmetrical. When we take a look at IQ tests, the lengths of crickets, yields of corn. So there are many other examples of real life data that's normally distributed, but that is just a few examples. So normal distributions, the reason that we use this normal curve and the normal distributions, they're good approximations for the results of many kinds of chance. Okay, so I talked about it's the probability and the area under the curve. So we're talking about chance outcomes, the number of heads in many tosses of a fair coin. Those are all approximately normally distributed. Also, many statistical inference procedures are based on the normal distribution, and that's what we're going to get into later on in the unit. Take a couple examples. Towards the middle and end of the normal distribution. We're going to be using when we're asking about incomes and whether or not they follow the. So this section in this chapter is really important for your basis for the rest of the year. So when we're asking about incomes and whether or not they follow the normal distribution, you want to think about drawing that normal curve and say, okay, if I were to come up with all of the incomes, would they form a nice normal curve? No, they're often skewed to the right with a lot of people making smaller amounts of money and few managers and CEOs making more. All right, so they're often skewed to the right. So most of your employees are going to make this much money, and then you have a few in the tails that are making more than everybody else. All right, do you think the heights of males follow a normal distribution? So you're going to kind of want to think in general about the heights of males. All right, if I were to plot 1,000 males on a scale and then draw a curve over them, would they follow a normal distribution? Yes, there will always be a population of males that's a little taller or shorter than everybody else. So the majority of the males are going to be right in the center here, okay, where you have some people over here that are going to be a little bit taller and some people that are shorter, but most are going to be about in the same range. All right, just remember that symmetric does not mean normal. All right, you can have a curve that is symmetric but not normal. So take a look at a bimodal curve that is symmetric, but it is definitely not normal. Okay, so it has to be unimodal and symmetric for it to be normal. Okay, so I can have a bar. I can also have a curve that is uniform. So remember that uniform curve that we talked about? Okay, where all bars are the same height. It's also symmetric, but it's definitely not normal. Okay, so how exactly can we tell if a distribution is normal? There are many normal curves. They can all look just slightly bit different, but they're all going to have a few properties in common. One is the 68, 95, 99.7 rule, which I believe you should hopefully have heard of in Algebra 1 or Algebra 2. Okay, so let's take a look at the official definition of the 68, 95, 99.7 rule, which is also called the empirical rule. In the normal distribution, if you have a mean mu and standard deviation sigma, it tells us that about 68% of the observations fall within one standard deviation of sigma. So that means 68% of your observations fall between -1 and +1 standard deviation. So 0 is my mean because that's the center of my data. Here's 1 standard deviation, 2 standard deviations, 3 standard deviations, -1 standard deviations, -2 standard deviations, -3 standard deviations. About 95% of your data are going to fall within 2 standard deviations. Okay, this total area from -2 to +2 is 95%. And then about 99.7% of the observations will fall between -3 and 3 standard deviations of your mean. Okay, you're going to have a little tiny bit of area left in your tails over here because most of your data in a normal curve, remember, we don't really define it using the outliers, is between -3 and +3 standard deviations. Okay, so if we write this in here, we're going to say 68% of our data is within 1 standard deviation, and then within 2 is 95% of our data, and then within 3 is 99.7. And you could figure out what percent is within each category. So 68 here, we know that this is 34, and this is 34. Okay, see if you can take a minute and figure out what percent of your data are within each of these other portions of your standard deviation. What percentage are within the various intervals. Okay, so let's just take a look at one distribution and use the empirical rule to make an estimation. And use the empirical rule to make an estimation. So let's just take a look at your Iowa test scores. We had this on a previous slide. So the distribution of the vocabulary scores for 7th graders we said was close to normal. Now remember, it says the distribution is, here's our shorthand way, because mathematics, we always want to make stuff a little bit shorter, is approximately normally distributed. Remember that this is your mean and this is your standard deviation. So 6.84 is your mean, 1.55 is your standard deviation. So what I would like you to do is sketch the normal density curve for this distribution and label the percentages using the empirical rule. So when you sketch a normal density curve, what you want to do, like I said, draw it before, draw your mean in the middle, and then what I want you to do is draw 3 standard deviations to the right of the curve and 3 standard deviations to the left of the curve. So go ahead, take a minute and try that. Okay, so let's just see how you did. All right, so number 1, what we have here is we have our mean right in the middle. Notice how we have the bottom labeled. What are we looking at? Okay, we're looking at the Iowa test. Okay, so here was our mean. Then to get the first standard deviation of the scores, I added 1.55. And then to get the second one, I added 1.55 again, added 1.55 again. To get to my below one, I subtracted 1.55. I took that number 5.29, subtracted 1.55. to get 3.74, subtracted 1 to get 2.19. All right, then you want to take a second and figure out what are all of the percentages in each of these portions. Okay, so we had said between one standard deviation was 68%, so we know that each of the portions here are 34% and 34%. And then we said within 2 standard deviations was 95%. Well, we've already used 68% of the 95, so we're just going to subtract the 68 and say, remember that that is divided between 1 and 2 standard deviations above and 1 and 2 standard deviations below, so we're just going to divide that by 2. So that gives us 13.5 on each side. Okay, and then we want to figure out between 2 and 3. So remember, within 3 standard deviations, we had 99.7. Okay, well, we've already used 95% of the curve up. So when we subtract that, we end up with 4.7. But that's going to be in my 2 above between 2 and 3. So I divide that by 2 and I get 2.35. All right, so how'd you do? Okay, so tiny bit take a look at that curve using those percentages, using the empirical rule. Listen to those directions. What percent of Iowa vocabulary scores use that to estimate how much of the area is under the curve between your various standard deviations? Okay. All right, so let's just take a look here. So we said what percent of scores are less than 3.74? Well, we had our curve labeled. Okay, if I shade in that area that's green, we had said that the area between 2 and 3 was 2.35, and then we had said this tiny little bit over here was 0.15. So about 2.5% of the scores are less than 3.74. Okay, so 3.74 is exactly 2 standard deviations below the mean. So based on the graph, when we add those two numbers together, we get 2.5%. So about 2.5% of the scores are less than 3.74. Notice that that's answering in context. All right, so let's take a look at C. Letter C says what percent of scores are between 5.29 and 9.94. In this case, we are using the empirical rule specifically to answer these questions. All right, so let's just take a look. Okay, we had 5.29 right here, okay, on my curve, and then I had 9.94 right here on my curve. So remember that we had those percentages. All we're doing is adding up our percentages. So we said that this was 34%, we said that this portion was 34%, and then we said right here was 13.5%. So all I have to do now is add these three percentages up. Okay, so 34 plus 34 plus 13.5 equals 81.5, and you'd want to make sure that you answer that in context. All right, so once again, let's take a look at the Iowa test density curve. Remember our same previous examples that it's normally distributed with a mean of 6.84 and a standard deviation of 1.55. So what percent of the students scored in 8.39? So think about that for a minute before you take a look at the answer. Let's see, where's that 8.39 located? Right there. How'd you do? You should have said none. Remember that when we're finding a percentage or an area under the curve, it is always going to be a range of values under the curve. We cannot calculate a percent at a single point because we're just calculating a height. In this case, there's exactly no width. All right, so what else is important about the empirical rule? Remember, the empirical rule is just an estimate. Please do not ever use the empirical rule unless it is explicitly stated use the empirical rule. It's not an exact area under the curve. We're going to investigate how to find the exact area under the curve next. For the future, and I just said this, if you're asked to estimate an area under the curve, do not use the empirical rule unless the directions specifically state to do so. All right, also please remember this, the empirical rule only applies to approximately normal distributions. So all the calculations that we've been talking about from now on are from approximately normal distributions. Keep in mind, no real life distribution is going to be perfectly normal, but approximately normal distributions. So why do I have this distribution right here with a big X through it that says don't use this? This is a distribution that's skewed to the left. The empirical rules and everything that we're going to be talking about do not apply to distributions that are right skewed and left skewed, because remember, the mean and the standard deviation are not good measures of center and spread. It's the median and the IQR, and the empirical rule is specifically based off the mean and the standard deviation. Okay, let's just suppose that we have a distribution of test scores that's approximately normal with the middle 95% of the scores between 72 and 84. What are the mean and standard deviation of this distribution? Now, the directions at the top say practice with the empirical rule. Unless it specifically says empirical rule, please do not use the empirical rule to do this. All right, so we're using the empirical rule to find out what the mean and standard deviation are. All right, so let's just take a minute and draw our curve. All right, like I said, always draw your curve, draw your mean down the middle, okay, and then you have 1 standard deviation, 2 standard deviation, 3, -1, -2, -3 above and below the mean. All right, so we know that 95% of the data is between 72 and 84. So we know 72 and 84, since it said 95% of the data, that is going to be within 2 standard deviations above the mean. So what is the spread from 72 to 84? Well, that spread is going to be 12. So if I just take 84 minus 72, that gives me 12. Well, how many sections does that 12 have to be divided into? So, because I know that this is 1 standard deviation, 2 standard deviations, 3 standard deviations, 4 standard deviations, if I divide that 12 by 4, that gives me 3. So that tells me that my standard deviation is 3. So if we take a look over here, if I do 78 plus 3 to get to the first standard deviation, plus 3 to get the second standard deviation, subtract 3, that gives me my range of 72 to 84. The next question says, can we calculate the percent of scores that are above 80? Oh, this can be a little bit tricky. All right, so if we did using our empirical rule, we know what percentages. We know between one standard deviation is 34% and 34%. We know that this was 13.5%. And then we know between 2 and 3 standard deviations was 2.35. But it says, what are the scores above 80? Well, 80 isn't one of my numbers that I have from my mean and my standard deviation. It's going to be right here. Here's where 80 is going to be. So I can't. Okay, so all normal distributions are the same if we measure in units of size. But what about this sigma percentage from between 80 and 81? It doesn't exactly follow the empirical rule, so we have to figure out exactly how many standard deviations it is from the mean measure to get my area. This is where we're going to start using in order to find the area under the curve. Bring back any memories? Okay, so the standard normal distribution is the normal distribution with mean, 0, and standard deviation of 1. So a normal distribution is just you taking the mean and standard deviation from your data and labeling it on the curve. The standard normal distribution is saying, okay, let's find the z-scores of the mean. Let's find the z-score of the first standard deviation, the second standard deviation, the third standard deviation. When you do that, the z-score of the mean is going to be 0. Because remember, your z-score is how far is it from the mean? Well, if it is the mean, the distance from the mean to the z-score is going to be 0. Okay, so if a variable x has any normal distribution with a mean and a standard deviation, then the standardized unit of measure is your z-scores. Okay, so when we draw a curve with the z-scores, it has the standard normal distribution of mean of 0 and standard deviation of 1. So just a quick example, let's just say that we have right here, we have a mean of 3, and then the standard deviation is 5. I lied, the standard deviation is 2. Okay, so every time you're adding or subtracting 2. This would be the normal distribution. The standard normal distribution would be the mean is 0, and basically what in that case it's doing is it's finding the z-score. What is the z-score of 3? So that would be, what is the mean? What is my data point? It's 3, because that is the mean, minus the mean, which is also 3, over the standard deviation, which was 2, which gives me a z-score of 0. So that's where the standard normal curve comes from. And this plus 2, this is exactly 1 standard deviation away from the mean. This is plus 2 again. This is 2 standard deviations away from the mean. Plus 2 again, that's 3 standard deviations away from the mean. So when we specifically talk about the mean of 0, which is basically a z-score of 0, and the z-scores of the 3 standard deviations above and below the mean, that's where we get the standard normal curve. Okay, basically the standard normal curve is all z-scores. Okay, so there's my graph. Sorry, it went on top of my writing. So what is a standard normal table? So because all normal distributions are the same, when we standardize them, okay, or make them into z-scores, we can find the area under any normal curve from a table. Now you have this table, it was part of your printouts that you needed to do at the beginning of the year, but you can also find it in one of the sections in Blackboard. Okay, so what is a standard normal table? So table A, or it's a table that you have that you should print out, is a table of areas under the standard normal curve. The table entry for each value of z is an area under the curve to the left of z. All right, so for example, let's say here, okay, we have our normal distribution, 0, we have a z-score of 1, 2, -1, -2. If I want to find an area less than 1, okay, the standard table, that standard normal table, always gives you the area to the left of a specific z-score. Okay, so let's just suppose that we want to find the proportion of observations from the standard normal distribution that are less than 0.81. Okay, so that's sort of what we talked about. We can use table A. All right, so the first thing we want to do is we standardize that curve, and we want to say what's the probability that z is less than 0.81. That's important here. Okay, specifically write out that probability. What are we looking for? The probability that z is less than 0.81. Okay, well, how did we get the fact that the probability is less than 0.81? Take a look at your table. Okay, the column on the left-hand side here is going to be your tens digit. Okay, your tens digit, so that's your 0.8. Go over, because we have 0.8, and then find the 1 under the column. So the row is the 0.8, the column is the 1. All right, so find where they match up. So you're going to go 0.8 and then 0.81, follow it in your table. That says 0.79. That 0.79 tells you that the area under the standard normal curve less than 0.81 is 79.10%. Okay? So always remember. So what I'd like you to do is take a look at the standard normal curve. We're going to find the proportion of observations from the standard normal distribution that are between negative 1.25 and 0.81. Now remember, when you're using the table, it's always talking about the area to the left. Drawing a curve and shading in the area will help you remember this. Okay, so we're looking for the proportion of observations between negative 1.25 and 0.81. All right, so let's just take a look at this for a second. If we find the proportion less than 0.81, or I look up 0.81 on the table, that's going to be the area to the left of 0.81. So that's 79.1% or 0.719. If I then do this, okay, if I look up the z-score of negative 1.25, that's also going to be the area to the left of negative 1.25, which is down here. However, I want the area between negative 1.25 and 0.81. So I want sort of this area in between here. I don't want this little portion down here. However, if I find the area of this little portion down here, can't I subtract it from the whole thing? So if I have this whole thing and subtract what I don't want, I have what's left. So the area between negative 1.25 and 0.81 is the entire area that we had got, 0.719, minus this portion that I chopped off. Okay, can we find the same proportion using a different approach? Sure. Okay, so another way to do this is I have my area shaded from negative 1.25 to 0.81. All right, so first of all, I already found out that the area over here, the area to the left of negative 1.25 is 0.1056. This is what I don't want, okay? I knew that this whole area less than 0.81 was 0.7910. So I could figure out what this area was because it was the whole curve. I could do 1 minus the whole area that I hadn't read up here to get 0.2090. All right, so when I find this area that I have shaded in red, what do I not want? I don't want this area that's in white, and I don't want this area that's in white. So remember that the whole area under the curve is 1. So if I take 1 minus the area that I didn't want in white over here, plus the area that I didn't want over here, I can do 1 minus both of these white areas to give me the area in red, which is 0.6854, which is the exact same answer that you got here. Okay, so you can use the tables. However, I would personally suggest you going and using your graphing calculator to do this. Please go to the graphing calculator section and see the calculator examples for notes on how to do this. All right, so number 1, your calculator is going to be much quicker than your tables, so I would suggest using it. And then number 2, just keep in mind when you use your calculator, you still are going to have to show your work, which is what I will show later on in the next couple of slides, what work you will need to show. So before you answer any of the questions, whether you're using your calculator or the table, please make sure you draw a sketch of the graph, shade in the appropriate area under the normal curve. It's going to help you find the area understand what area you're finding. All right, so what I would like you to do is try using a calculator to find the proportion of observations from the standard normal distribution that are less than 0.54, greater than negative 1.12, greater than 3.89, between 0.49 and 1.82, and within 1.5 standard deviations of the mean. Okay, so on your graphing calculator, all right, please go look at the calculator examples for notes on how to do this. All right, what you're going to do is, this is just a really brief example. When you hit second vars, notice at the top it says distra. That's looking at a distribution. Then you're going to go down to number 2. It says normal CDF. Okay, what does that mean? That's telling you you're looking at the normal curve. CDF means cumulative density function. What does cumulative density function mean? That means find the area under the curve. Do not use the number 1. Okay, that's finding a single point, which you can't do. So how does normal CDF work? Once you press enter on your calculator, it's going to come up and it'll say normal CDF. Okay. It wants your lower bound, your upper bound, your mean, and your standard deviation. Well, what does that mean? Okay, so normal CDF, if I typed in this, okay, if I typed in the lower bound of negative 1,000, an upper bound of 2.3, our mean is 0 because we're talking about the standard normal curve, that was right here, and the standard deviation of 1. Okay, so remember with the standard normal curve, it's always approximately normal with a mean of 0, standard deviation of 1. Okay, so what this tells me, if I was to draw a curve here, this basically tells me find the area under the curve or the probability that x is less than 2.3. Well, where did that come from? If this is my lower bound, negative 1,000 is like all the way down here. Okay, 2.3, that's my upper bound. Okay, so there's my 2.3 that has a mean of 0 and a standard deviation of 1. All right, so I'm specifically looking at the curve that has a mean of 0 and standard deviation of 1. Okay, so that's just a quick summary. Go ahead and look at your notes in order to find the actual instructions on how to do that. Try this and then take a look at the next couple slides for your answers. Okay, so just a couple of hints and tips. Number 1, please make sure you round to 4 decimal places for accuracy. Okay, that's the first thing. After you've used your calculator to find the proportion of observations, please, please, please make sure that you write the probability statement. Okay, these are already in z-scores. All right, these are already in z-scores. You have to include this probability statement. So what did you find? You found the probability, since it was the standard normal curve of z, that z is less than or equal to 0.54. Okay, this is the probability that z is greater than or equal to negative 1.12. Include that probability statement. If you don't include that probability statement, it will be marked wrong. So this, just a quick example from your calculator, would have been normal CDF. Okay, we wanted greater than negative 1.12, so that was my lower bound. My upper bound, I'm just going to make up a really big number because I want it to keep going under the curve. The mean was 0 and the standard deviation was 1. Okay, and then for this one, your last one, D, your lower bound would have been 0.49 and your upper bound would have been 1.82. Okay, within 1.5 standard deviations of the mean. So if you're ever not sure, I always draw your curve. So that would mean I'm talking about negative 1.5 standard deviations and positive 1.5 standard deviations. So your lower bound would be 1.5 and your upper bound would be 1.5. Sorry, your lower bound would have been negative 1.5. And that gives you the area under the curve at that specific point. Okay, so how do we work backwards? So how can we find a z-score from a percentile? Just as a quick refresher, what does a percentile mean? A percentile, remember, means the area under the curve less than that specific number. Well, remember, if we're taking a look at z-scores from our table, okay, remember when we find the area under the curve from a z-score, it's always the area to the left, which is the area that's less. Okay, so let's just take a look at a distribution of test scores as approximately normal, and Joe scores in the 85th percentile. How many standard deviations above the mean did he score? So now we're given the percentile or the area under the curve, and we want to work backwards and find the standard deviation. Draw the curve first. Okay, please, please, please draw the curve first. All right, so we're drawing it. We're labeling right here, this is my z-score because I don't know what it is. I have the 0.850 because 85th percentile means here's where he is, here's Joe. Okay, here's Joe, but he scored in the 85th percentile, so that means 85% were less than him. How did I get this z-score of 1.03? Okay, we know the area under the curve, but we don't know the z-score. We know it's 0.85. Okay, you're going to use your calculator. So on your calculator, you're going to hit second distribution, the same thing that we just did in the last section, and you're going to hit inverse norm. Well, what does inverse norm mean? Inverse norm means find the opposite. It means do the inverse or the opposite. In this case, you don't have the z-score, you have the area. You type in the area and it will give you the associated z-score. Just like with z-scores, the inverse norm always gives you the area to the left. So if you type in inverse norm of 0.85, it's going to give you a z-score of 1.03. Okay, so just please keep that in mind. It's always the area to the left. Think about this for a second. Okay, let's say I know that this area is 20%, but I want this z-score. You're not going to type in inverse norm of 0.2 because that would mean 0.2 would be down here, it'd be everything to the left of 0.2. So you'd be typing in inverse norm of 0.80. Okay, we'll be going over that a little bit more in a minute. I just wanted to show you. You can also use your table to do this. So on the table, you would find the percentage. Okay, so you'd find the percent of 0.85 and then look at your table and find your z-score. Okay, so let's just take a look at two quick examples. All right, so take a look at question 1. So in a normal distribution, quartile 1 is how many standard deviations below the mean? So see if you can answer that based on what you know. And then take a look at question 2, and then we'll go over the answers. Find the z-score that corresponds to the given area on the curve. Remember that percentile and inverse norm is always going to be the area to the left. Okay, personally, I would always draw a picture. Please always draw a picture. Always, always, always draw a picture. Okay, so I would do this. So quartile 1 is how many standard deviations below the mean. So that's asking us, well, what is the z-score? Okay, here's your mean of 0. Quartile 1 is what percentage? Remember that quartile 1 is the 25th percentile, so that means that 25% of your curve is going to be shaded. Okay, so if this is 25% of your curve, what is this z-score? All right, so on your graphing calculator, you're going to type in inverse norm of 0.25 because that's saying that's the area to the left. And when it gives you negative 0.6745, it means that the 20th percentile is 0.6745 standard deviations below the mean. So when you do inverse norm, it's always giving you saying, okay, I have the area below my number is 0.25. What's the associated z-score? All right, so this one, find the z-value that corresponds to this area. Oh, here's my z-score that I want to find, but notice it's the area to the right. So if I type in 0.8962, that's going to give me the area to the left. Okay, I don't want the area to the left. I want this specific z-score right here. Okay, so when I type in inverse norm, I need to make sure that the area is to the left of my z-score, not the right. Right here, the area that I'm given is the area to the right of the z-score, not the area to the left of the z-score. All right, so how do I get that area to the left? I'm going to do 1 minus 0.8962. Ooh, so now I have that area to the left is 0.1038. Then on my calculator, I can do inverse norm of 0.1038, which is negative 1.26. Okay, and if you're going to use the table, do the same thing. You have to find what is the area to the left of your z-score. So right here, this is the area to the right. I don't want the area to the right. I want the area to the left. Okay, you'd have to subtract and then look up 0.1038 in your table and then find the corresponding z-score. Okay, so how do we solve problems involving normal distributions? So you need to make sure you understand and follow these steps, and this is going to be really important. There are 7 steps that go with this. Okay, number 1, whenever we're talking about finding, if it says find the area under the curve, you need to make sure that you state these couple of steps. There'll be 7 steps associated to them. Number 1, state your variable of interest. You need to specifically state that it's approximately normal. What's the mean? What's the standard deviation? So that the person that you're talking about knows you're talking about the normal curve. Draw a picture of the distribution. Shade the area under the curve. Then you're going to do the calculations. Number 1, since our tables or calculators are based on z-scores, find the z-score, show your work. Then make a probability statement. So make sure that you write a probability statement. What area are you finding under the curve? You're finding the area under the curve, the probability that z is less than negative 1.2. The area under the curve is less than negative 1.2. Write your conclusions in context. Okay, and then so make when sure you're doing these types of questions, when you're doing normal distribution calculations, do please avoid calculator speak on the AP exam and on your homeworks and your tests and quizzes. There are many calculators that speak many different languages, and if you just write normal CDF, this is my lower bound, upper bound, my mean is 104, my 8 is my standard deviation, it will be marked wrong, okay, because the readers of, you can't assume that the readers of the AP exam know what calculator you used. You must show your work, and it will be demonstrated on the following slides what work you'll need to show. Okay, so let's take a look at this example. This example, I'm going to go through one, and then you guys can just get some practice problems. Demonstrates the steps that you'll need to show. So when Tiger Woods hits his driver, the distance the ball travels can be described by the normal distribution with a mean of 308 and a standard mean of 304 and a standard deviation of 8. What percent of his drives travel between 305 and 325 yards? Well, remember, the only thing our calculator and our table uses is z-scores. Okay, so the first thing you're going to do is draw your curve. Label the mean, use your standard deviations to label 3 above and 3 below, and shade your area. So our area is between 305 and 325. Okay, I have my first step done. I've drawn my curve. I know what it looks like. The second step is make sure that you write specifically what we're looking at. So step 1, okay, write it's approximately normal with a mean of 304 and a standard deviation of 8. Then, from your curve that you've drawn, what probability are you finding? What percent under the curve are you finding? You're finding the percent between 305 and 325. Okay, so you want to include that, the probability, the percent under the curve that x is between 305 and 325. Okay, the second step is we have to standardize that. All right, so what is the z-score for 305 and 325? Show those calculations. You must show them. All right, so here's my 2 calculations. So this one down here is 0.13. This one over here is 2.63. So then what area or what percentage are we now finding with our z-scores? So we're now finding the percentage that z is between 0.13 and 2.13. So normal distribution, first percentage using your values. Find the z-scores, then the percentage using your z-scores. Okay, finally, you can then use your graphing calculator to get your answer. So about 44% of Tiger's drives travel between 305 and 325 yards. Notice that is in context. Okay, so how would I have written that on my graphing calculator? So I would have done normal CDF. Okay, and you don't have to write this calculator speak. So my lower bound was 0.13, my upper bound was 2.13, my mean was 0, standard deviation of 1, and that's going to give you about 0.44. Okay, so just
go ahead,
take a minute and try these. Exactly what
go ahead and read this,
pause it, read it, and then I will show you the answers on the next slides. Okay, so I'm going to show you the answers. So just pause if you need more time and then press play when you're ready to see. Okay, so the first one, letter A, was what proportion of his first serves would you expect to exceed 120? All right, so when you have a question like this, you can put the parameter statement or telling the reader that it's approximately normally distributed with your mean and standard deviation at the beginning. So if you have multiple parts to a question, you only need to write that once. That's totally fine. So what proportion of the serves would you expect to exceed 120? So here's the steps that we talked about. First, the probability statement, greater than 120. Draw your curve, label it. Okay, here's your mean of 115. 120 is bigger than that. Shade it so you know exactly what you're doing. Okay, here's your z-score. So your probability statement using the given information, find your z-score, probability statement again using the z-score, okay, and then this, I would use your graphing calculator to get it, but if you're going to use your table, okay, remember that it's always the area to the left of the curve. So then, answering in a sentence, about 20.23 of Nadal's first serves would exceed 120 miles per hour. So take a look at the second one. You don't have to write that if you've already done it. Your probability statement, work for both of your z-scores, probability statement with your z-scores, answer as a sentence, and your picture drawn, okay, with the area shaded. If you're having some questions on how to find that probability, either using your calculator or your tables, please just let me know. Okay, this one was a little bit trickier. It said the fastest 30% of Nadal's first serves go at least what speed? All right, so here's what we're talking about. Number one, so we want to know what speed they go. We know it's approximately normally distributed, 115.6, okay? All right, so we know that this is 115 and it's we have a standard deviation of 6. Now, when we say the fastest 30% of the scores, when we draw this curve, it's 100% of his serves. So here's where the fastest 30% go. Here's where the everything's slower than that. All right, now, when you're asked to do that, you have to find that z-score. So basically, it's asking me to find what is my z-score. But remember, when you type in inverse norm, it's always showing the area to the left of the z-score. Well, what is the area to the left of the z-score? It's 70%. So you want to type in inverse norm of 0.70, and that gives you a z-score of 0.5244. If you type in 30%, okay, if you type in inverse norm of 0.3, that's like saying, okay, only 30% of the area shaded is going to give you that z-score down here. That's not what you want to do. Now, this gave you the z-score, so now you have to work backwards to actually find the first serve. So remember, your formula is your z-score minus equals your data point minus the mean divided by the standard deviation. So we know the z-score, we know the mean, we know the standard deviation. What we're trying to find is our x. You have to show that work. Okay, that should not have a bar on top of it. You have to show that work. So then answer is in context, the fastest 30% of Nadal's first serves go at least. Last question says, what is the IQR for the distribution of Nadal's first serve speeds? Okay, so once again, I would draw it. So remember, your IQR is between 25 and 75%. Draw that. Okay, now here's what we're doing. So we're finding the inverse norm. So I have to find out what this z-score is and this z-score is. So remember that, okay, to find this z-score right here, I'm going to do inverse norm of 0.75 because that is 75% of the area is to the left of that. I can also do inverse norm right here of 0.25 because I still know that this is 25% of the area of the curve underneath it. So to the left of that z is also 25%. Okay, so then once again, you're going to kind of work backwards here. So remember, I'm sorry, I'm not sure why these bars are here. Okay, remember that this is your z-score equals your data point minus your mean divided by the standard deviation. So after you have the z-score, you're going to work backwards to actually find the data point. So to get our IQR, all right, it's 119.047 minus 110.963 to get our final answer. Okay, so the normal distribution provides some good models for distributions of real-life data, such as SAT scores, IQ scores, highway gas mileage, unemployment weights, and weights of bags of potato chips. Many statistical inference procedures are based on the assumption that the population is approximately normally distributed. So we've been using normal distribution calculations. How can we tell if the data is approximately normally distributed? Well, we have three different methods. Okay, number one, we can plot the data and look and see if it follows an approximately normally distribution. We can do that using a dot plot, or a stem plot, or a histogram to see if the graph is symmetric and bell-shaped. Do not use a box and whisker plot. Okay? We can check to see whether the data follows the 68, 95, 99.7 rule. That means that 68% of the data is within one standard deviation, 95% is within 2 standard deviations, and 99.7 is within 3 standard deviations. Okay, how do we do that? We physically count how many observations that fall within 1, 2, or 3 standard deviations and check to see if these percents are close to 68, 95, and 99.7. They're never going to be perfect. You're going to have to use your good estimation skills to say, okay, if this is really far off, or hey, it's pretty close to the approximation, therefore it's approximately normal. The other way to do this is something called a normal probability plot. They are constructed by plotting each observation in a data set against its corresponding percentiles z-score. Okay, so we take a look at each observation and then we find the z-score based on the percentile. You will never have to do this. Your calculator will do this all for you. Please make sure that you take a look at the calculator instructions that are in this section on how to find the normal probability plot. Okay, so once we've have this normal probability plot, how do we interpret them? If the points on a normal probability plot lie close to a straight line, this indicates that the data are normal. A few deviations from a straight line or systematic deviations from a straight line indicate a non-normal distribution. Outliers will appear as points that are far away from the overall pattern of the plot. Okay, so let's just take a look at what this normal probability plot looks like. So here is skewed data. This is skewed to the right. Okay, if I draw the normal probability plot, so the normal probability plot, remember, is the observation, okay, and then you're plotting it against the corresponding percentile z-score. All right, so if you take a look at this, okay, my data is all, if you take a look at the z-scores, okay, they're all of them are in a pretty low percentile. They're all bunched together. So since they're all bunched together, that's going to indicate that the data is curved on the left-hand side. Take a look at the long right tail. That's going to tell you that it's skewed to the right. Okay, when we're looking at normal probability plots, don't worry about minor wiggles in your graph. We're looking for shapes that are clear departures from normality. A normal probability plots, please understand, are not on the AP topic outline. However, they're useful for assessing normality. You can use them on the AP exam, just make sure you state that you're specifically looking for a linear pattern. So here's sort of your same example. Take a look, the largest observations fall far to the right of the line, therefore it's right skewed. All right, so if I was to make this linear, I have all these observations over here in the tail. Okay, so these are like really high percentiles. Okay, so I have a lot that are in really high percentiles, so that sort of shows us that it's not approximately normally distributed. Okay, so what do I want to look for? Let's take a look at this approximately normally distributed graph. Okay, you have your x values and then you have your percentiles, the corresponding percentiles. It's in a nice straight line. that tells us that it's approximately normally distributed. And you want to state, since the normal probability plot is linear, the data is approximately normally distributed. What does it look like if it's strongly skewed to the left? Well, think about this. There's going to be a whole bunch of points over here in the tail that are in a really low percentile, where all these points over here are going to kind of be in a really high percentile. So they're going to kind of be bunched in that high percentile. They're not going to be nicely sort of spread out. All right, so what does that graph look like? So notice how you have all these points that are in a left tail. There's a curve over here. It's not perfectly linear because I have all these points on the right-hand side that are in a higher percentile, and these points on the left-hand side that create this left tail over here. Okay, the data is bunched on the right, just like it's bunched on the right on the graph. So the largest observations fall to the left of the line, which is up here. Okay, so what I'm going to have you do is you're going to practice assessing the normality. So here are some measurements listed below to describe the usable capacity of a sample of 36 side-by-side refrigerators. We want to know, are the data close to normal? Number one, what I'd like you to do is go to your calculator notes, learn how to graph a normal probability plot. It's very easy. It's literally just the other scatter plot when you're choosing what plots to graph, okay, but you have to make sure you enter the data in your calculator. You're going to plot the data on your calculator and then answer the question. Please plot it using a histogram, then calculate the data using the empirical rule, and then use the normal probability plot to determine if the data is normally distributed. Justify your answer means explain why the histogram tells you it is or is not, why the empirical rule is or is not, how the normal probability plot tells you is or is not. Okay, so take a minute, pause this, try it, and then we'll go over the answer. Okay, so here's our histogram. Here's a histogram of the data. Make sure you state it seems roughly symmetric and bell shape. Make sure you include your labels. All right, so that's one piece of evidence. The second piece of evidence is our empirical rule. The mean and standard deviation, which we found from our graphing calculator. Notice I'm X bar and S of X from your graphing calculator because they are sample data. So we found, notice the work that's shown here, X bar plus or minus 1 standard deviation, X bar plus or minus 2, X bar plus or minus 3, and then gave us the intervals. I counted how many of the data points were within each interval, calculated the percentage, and then gave a conclusion. So the percents are quite close to what we would expect based on the rule. So combined with this graph, they give us good evidence that it's close to approximately normal. Okay, so let's just check the last thing, the normal probability plot. It's actually probably one of the easiest to use. So just make sure you've checked your calculator instructions on how to do this. So here's the normal probability plot. Remember, it's the actual value plotted against the expected z-score. So here's your normal probability plot. Sometimes you'll hear it called a normal quantile plot. It's quite linear, supporting our decision that the distribution is close to normal. So it's just important that you say it's about linear. Okay, make sure that you state it's linear, therefore approximately normally distributed. Okay, so that was a long section. Here's just a quick summary. So we learned about the normal distribution using normal curves. We learned about the standard normal distribution, which was 0 and 1 for our mean and standard deviation. We took a look at the empirical rule. Okay, we took a look at the standard normal distribution. We took a look at table A and percentiles, and then we took a look at how we can decide whether or not something is normal. If you have any questions, please let me know.